Hello, everyone. Today we have a speaker from UK joining remotely in the evening over there. So our speaker today is Dr. Lin Qiao. Lin is a postdoctoral assistant at Queen Mary University of London in computational astrophysics group with Dr. Thomas Howard. Tom Howard is my actually one of the closest collaborator, and I met Lin a couple of years ago, and it was really nice to hear about her work, so I invited her here. So Lin works on planetary disk evolution, especially on the effect of the environment, like external photo-evaporation, and also work on the pebble accretion, basically modeling how small pebbles, so pebbles actually, and the accretion and the planetary formation actually get affected by environment as well. And so we're here today about this, I think it's clusters environment, right? So Lin, the floor is yours.
Hi everyone, thank you so much for the introduction and thank you so much for inviting me to the Origin seminar. So yeah, today I will present my research on looking at how disk evolution and planet formation are affected by stellar cluster environments. Okay. So first of all, just for a little bit of a background introduction, there are now overwhelming evidence that planets form in disks around young host stars that are still part of the collapsing star-forming regions. And there are different types of star-forming clusters as the natal birthing environments for protoplanetary disks and planets, characterized by different masses. So there are low mass star forming regions, like our nearby star forming regions, such as Taurus or Lupus, that only contains hundreds of stars without any massive stars. There are also massive star forming regions, such as ONC and Carina, that contains a handful of massive stars with higher stellar densities, with massive stars giving off radiation and stellar feedback in the cluster. And there are also those supermassive star-forming regions that contains numerous massive stars. They have extremely high stellar densities and giving off extremely high levels of radiation from massive stars that's contained within them. And although currently most of the disk observations that we are very familiar with are made in the nearby low mass star-forming regions, it is these more massive types of star clusters that actually represent the more typical star-forming environments where most of the stars and therefore planets around them are formed. So in order to demonstrate the typical type of star-forming environments where most of the stars form, here is a theoretical analysis of the distribution of different types of star-forming regions and the distribution of stars in these types of star-forming regions. So in this plot, the black points represent a subset of 1,000 of synthetic star-forming regions being sampled. And on the horizontal axis is the number of stars in a cluster, and the vertical axis represents the FUV luminosity of certain star-forming regions. And the color scale indicates the fraction of stars that form in different star-forming regions. And you can see that on the left-hand side of this plot, you would have lots of star-forming regions, but each star-forming region doesn't contain many stars in them. On the right-hand side, on the other hand, there are not many supermassive star-forming regions, but in each star-forming region, they contain a lot of stars in them. So from this sort of analysis, you can see that although there are more number of low-mass star-forming regions on the left-hand side, but more stars overall are actually formed in the massive star clusters. Because in the massive star clusters, there are just the number of stars in each of them are just very, very numerous. So this is a massive stellar cluster formation feedback simulation from Matthew Bate. simulated from the collapse of a giant molecular cloud. And you can see that stars starts to form in these filamentary structures. You'll see it in a bit over time. And as the cluster evolves, numerous stars form in these clusters. Yeah, will happen soon. Yeah, you can see the stars starts to form in these filaments, and over time, numerous stars form and get scattered, and the strong stellar feedback from these massive stars in the cluster also disperse the gas and forms feedback bubbles over time. So in these massive stellar clusters with high stellar densities, very strong levels of radiation, and stellar feedback from the massive stars, disk evolution and planet formation can be affected by many things in these kind of natal cluster environment. So one of the ways is via external photoevaporation induced by the far UV radiation from the massive stars in a cluster, which strips planet-forming materials from the disk and cause rapid radius truncation. This can also be affected by dynamical truncations by frequent stellar flybys in this kind of cluster. There can also be ongoing inflow of star-forming gas cloud onto the disk, kind of then replenishing the disk material. And the radiation from the massive stars and the cosmic rays, for example, reaching the disk surface, can alter the disk chemistry and therefore alter the planet compositions. For this talk, I will focus on the first effect, which is the external photoevaporation. Therefore, in order to understand the observed diverse exoplanet population and diverse planetary architectures that we observe, it is not enough to just study disk evolution and planet formation as isolated systems. Understanding the impact of the diverse planet birth environment is also important. So just for a very brief overview of external photoevaporation, this happens when a massive star in a cluster give off strong FUV radiation that reaches all the way to a disk around a host star. And the FUV radiation heats the disk surface to a high enough temperature so that it reduces the gravitational radius of the disk. So the gravitational radius is a critical distance beyond which the orbiting disk material can thermally escape from the host star's gravity. So the FUV radiation heats up the disk to a high enough temperature, reduces the gravitational radius of the disk so that a thermal wind can be launched from the disk surface in the outer disk edge region from beyond the reduced gravitational radius, stripping planet-forming material from the disk. So when this happens, the disk will suffer from photoevaporative mass loss and rapid disk radius truncation. So there has been plenty of direct observations of protoplanetary disks with externally photoevaporative winds, especially in the ONC, which is our nearest massive star-forming regions. These externally photoevaporated disks are observed as propylids all the way back in the early mid-90s. So propylids are circumstellar disks irradiated externally strongly enough so that it is enveloped in a cometary wind with a visible layer of ionized cusp towards the radiation source and a tail pointing away from the source. This is an artist's impression of a propylid. So on the right-hand side of this video is a massive external star giving off UV radiation that reaches the disk surface. So it launches a wind from the disk surface with this cocoon of thin ionization front with a cusp pointing towards the radiation source. So these are some examples of very nicely spectrally resolved images of propylids in the ONC from Muse VLT. And on the right-hand side, it is a cartoon of the anatomy of a propylid. In this case, the X-ray radiation source would be coming from the top of the page, giving off radiation that reaches the disk surface. And yeah, so then a neutral PDR wind is launched by the FUV radiation penetrating all the way to the disk surface. And the EUV radiation, the ionizing part of the photons, they're able to penetrate they're not able to penetrate all the way to the disk surface. Therefore, they kind of form this thin layer of ionization front. And also on this graph, there are different kind of observational tracers that traces different parts of the disk. So this is again another example of a stellar cluster formation and evolution simulation with feedback used in my study. The cluster forms from the collapse of the giant molecular cloud, and the color indicates the column density. And later on, you'll see the dots that would represent sinks of stars that are forming it. So you can see that as the cluster evolves, new stars are constantly generated. Stars also dynamically evolve over time, and the star-forming cloud gradually disperse over time due to stellar feedback. Therefore, for a disk in this kind of cluster, the FUV radiation from the massive stars in the cluster incident upon them changes as the cluster evolves. For example, if a disk around a host star is initially embedded in a dense gas region, the gas can then shield the FUV radiation for some time, protecting the disk from external photoevaporation before the cloud then disperses or the star moves dynamically out of the embedded region. Therefore, it is then again not enough to study disk evolution planet formation as isolated system, as I previously mentioned. It is important to study these processes in the context of cluster evolution. So the key questions my research aimed to address are at what stage of disk evolution does external photoevaporation happens? What are the shielding effects of the clouds? And how does the disk population in these clusters evolve as the cluster kind of evolve itself? So and to study this, I coupled the disk evolution model to a stellar cluster and formation and feedback model in order to determine how the interplay of stellar feedback, ongoing star formation, and cloud shielding together kind of influence the role of external photoevaporation of disks. Oops. Specifically, to do this, I used the star formation feedback simulation, starting from the class of the giant molecular cloud, like the one I showed in the previous slide. It is evolved for 2 million years, and for each star generated in this cluster, we track the FUV field history at its location over time in 2 ways. One via Monte Carlo radiative transfer, which would count in the effect of gas clouds attenuation of the FUV photons, therefore counting the cloud shielding effects. And for comparison, we also track the FUV field radiation incident upon the same stars with simple geometric dilution, neglecting the gas clouds attenuation of FUV field, therefore without counting the effect of cloud shielding. We then evolve a 1D viscous disk model with effect of external photoevaporation induced by its unique history of FUV radiation. And this is done for every star that's generated in the cluster. So I first looked at the statistics of the FUV field incident upon disks in the clusters. Now on the left-hand side panels shows the probability distribution of FUV field incident upon all disks that exist at a certain time snap of a cluster age. from top to bottom, it is cluster age of 0.5 million years, 0.8 million years, 1 million years, 1.5, and 2 million years. So initially, in the cluster, we can see that there are two populations of the disk. One population that are embedded in the cloud, so experience initially a low FUV radiation, and another population that are already exposed to high FUV fields. And as the cluster age increases, the more material gets dispersed by stellar feedback and more radiation sources form. So more disks then ends up with high FUV radiation field incident upon them. And the two population gradually merges into one population just centered around a very high incident FUV values. Now on the right-hand side panels are different from the left-hand side. They're the plots of FUV distribution incident upon disks with a certain disk age in each plot. So instead of looking at all disks at a certain cluster age snapshot, like the left-hand side ones, here we're looking at FUV field for all disks that have lived, for example, on the top plot for 0.5 million years throughout the simulation. But they could have born, for example, at any time in the cluster age. And these plots highlights actually, even for stars that have evolved for only 0.5 million years, most of them are already exposed to a pretty high level of FUV field for the cluster simulated. So that it shows that overall, shielding act for a short time for most of the disks in the cluster. But here's an example of a disk evolution history around a particular host star in the cluster simulation shown in the previous slides. On the top plot, top left plot, the blue curve shows the FUV incident upon the disk as a function of time as the cluster evolves. The disk is, you can see in this case, is initially shielded for approximately 0.8 million years before being exposed to a strong UV radiation. The orange curve shows the FUV radiation upon the same disk location if we neglect the gas cloud's attenuation of the FUV field. And by the way, for the unit of the FUV field strength, we normally use the Habing unit G0. It is a unit normalized to the value of the average FUV radiation strength in the ISM of our solar neighborhood. So now on the right-hand side, the top and bottom panel shows the cumulative mass loss on the top and the evolution of disk radius for the same disk but evolved under external photoevaporation with or without counting into the impact of the cloud shielding. And you can see that while the disk is shielded, it is protected from high mass loss rates and rapid disk truncation before the cloud disperses, then exposing the disk to strong levels of radiation. So this shows that although most disks in the cluster are shielded for a short period of time, but for those that have early cloud shielding, it can be important for the early stage of disk evolution. And later on, I will show that this initial cloud shielding period is important in facilitating planet formation via pebble accretion. I also looked at the disk population statistics at different cluster ages. Here we have the plot of the inverse cumulative distribution function of dust mass for disks that exist at different cluster ages. The blue curve shows the dust mass from the simulations, and the yellow curve kind of converts the simulated dust mass to an observer's equivalence of dust mass. Again, the solid lines shows the disk evolved counting into the gas cloud shielding effect, and the dotted curves are the same disk evolved neglecting the cloud shielding effect. And the green and red curves are just the observed data from Lupus and ONC, just overplotted for reference. And for these plots, you can see that comparing the difference between the solid and dotted curves, cloud shielding has the most impact around the cluster age of 1 million years for the specific cluster that we simulated, when at this age the strong UV sources have formed, but the cloud, but most of the star-forming clouds in the cluster are not yet widely dispersed. And very similar story for the disk radii distribution as well. I also looked at the propylifraction of the disks in the cluster. This is a plot of the number of propylids by the right curve and the propylifraction by the blue curve of the simulated cluster. So you can see that for the propylifraction, it becomes quite high as the cluster evolves. So our model predict widespread photo-evaporation in a carina-like environment. I should mention that for the cluster we simulated, it's 10 to the 5 solar mass, so it resembles approximately the mass of carina-like cluster. So now, given that I have demonstrated that the disk evolution can be strongly affected by external photoevaporation in a stellar cluster, it naturally then leads to the question of how does planet formation in such disks affected by their natal cluster? If external photoevaporation mainly, sorry, sorry, just the lights in my room just went off.
But you need to move, I guess.
Sorry, okay. And now we're back. Yes. Sorry, yeah, continue. So yeah, so there are questions like if external photoevaporation mainly strips disk material from the outer disk region, and planet formation mainly happens in more of the inner region of the disk compared to where external photoevaporation operates, would the external mass loss still affect planet formation? So for the second half of my talk, I will talk about my research on how planet formation via pebble accretion is affected by external photoevaporation. So now for a brief overview of the mechanism of planet formation via pebble accretion. On the left-hand side figure is an illustration of how planetary embryos grow via pebble accretion. So in a disk, we have dust grains that grows into pebbles at the location of pebble production front at a certain time. Pebbles are produced at the pebble production front and drift inwards. And because the dust growth timescale is shorter for dust at smaller radii, the dust at inner disk grows to pebble size first, so the pebble production front moves from inside out. The embryonic cores accrete from the flux of the inwardly drifting pebbles produced at the pebble production front, and over time grows and migrate. The growth stops when the pebble production front reaches the disk outer edge. Therefore, the pebble flux then gets cut off because all the dust in the disk then have finished converting to pebbles. So now on the right-hand side figure is a qualitative description of the mechanism of how external photoevaporation can affect an embryonic core growth located at the inner disk region. So if the disk is subject to external photoevaporation, the outer disk can be truncated rapidly, so that the time it takes for the pebble production front to reach the truncated disk outer edge would shorten significantly. So this reduces the pebble mass reservoir in the disk available for embryos to accrete, therefore limiting the planet's growth potential via pebble accretion. However, if the disk is initially shielded by the star-forming cloud for some time from high-level UV radiation first, it can then preserve the pebble mass reservoir by delaying this rapid disk truncation. Indeed, in our simulation of planet growth via pebble accretion with a single embryo in a disk, first, that are subject to a strong level of FUV radiation, the effects of the initial shielding time are significant. So on this plot, it is a evolution of the planet mass on the y-axis versus the semi-major axis of embryos injected at different semi-major axis location indicated by different colors. By the way, these are all models of just right now a single embryo per disc case. And in the disc is irradiated by a strong level of radiation of 10 to the 4 G naught. And we can see that if the disk is not shielded, so shielding time equals to 0 million years, the embryos initially located further than, for example, 14 AU are not really able to grow at all. But as we increase the initial shielding time, then embryos at larger radii can grow to larger final mass. And on the right-hand plot, we're looking at on the top plot, the final planet mass as a function of shielding time, with different colors again indicate the embryos injected with different initial semi-major axes. You can see a non-linear correlation between the final mass the embryos are able to achieve as a function of shielding time up until a certain shielding time value. An embryo initially located at 25 AU, for example, are only able to grow to lunar mass if the disk is not shielded. But if it is shielded for 1.5 million years, it is able to grow to almost 10 Earth mass, for example. But these simulations so far is for only considering just one single planetary embryo per disk. So of course, in reality, there will be a lot more than one planetary embryos in a disk. So the embryos, they're subject to planet interactions among each other and planet migration as a consequence of for example, planet disk interactions and all these processes. So for the rest of the talk, I will focus on my research on then studying how the impacts of external photoevaporation in stellar cluster on affecting the formation of multi-planet system formation via pebble accretion, how that affect the evolution of the multi-planet system, and how external photoevaporation affect the resultant planetary system and planetary architecture. So in order to study this, we coupled a model of embodied planet formation from planetary embryos via pebble accretion with a model of 1D viscous disk evolution. So the planet formation model includes the process of planet-planet interactions, planet migration as a result of planet disk interactions, and it can accrete gas if the planetary core grows massive enough. And the disk evolution code is subject to external photoevaporation under the impact of a time-varying FUV field. And in order to, in this case, for a controlled study of the impact of cloud shielding time in facilitating planet growth, we decided to use a parameterized FUV track like the ones shown on the right-hand side plot. So in the parameterized FUV track, the FUV field would always start with a very low value for a period of time, period of shielding time, before it suddenly increased to a high level of radiation. So now just to demonstrate some of the results, on the left-hand side panel is a video of disk evolution and on the top plot and planet growth on the bottom plot via pebble accretion in a disk on the left-hand side right now that is subject to a very low level of radiation, therefore practically no external photoevaporation at all. And the top plot shows the evolution of disk surface density, and the bottom figure shows the planet mass against the semi-major axis. The red dots right now indicates the initial planetary embryo, and the color would indicate evolution time. So you can see that without external photoevaporation, the disk kind of just viscously evolve, and planets here are able to accrete pebbles and grows and migrate over time. Okay. Yeah. So now on the middle panel now shows the same disk, but now subject to a very strong level of FUV radiation of 10 to the 5 G0. And now you can see that with a very strong external photoevaporation, the disk radii gets rapidly truncated, and this acts to reduce the pebble mass reservoir in the disk. Therefore, you can see that the growth of the planetary embryos are greatly suppressed in this case compared to the left-hand side. Now, on the right-hand side panel shows again the same for the planet formation in the same disk, but in this case, the disk is again subject to the same level of radiation of 10 to the 5 G0 as the middle panel. But in this case, the disk is initially shielded for about 1.5 million years. And we can see that if the disk is shielded for some time first, then the embryos in this disk can have a head start on accreting pebbles and grows and migrates before the rapid disk truncation by external photoevaporation after the cloud shielding time. So similar to the case of the single embryo per disk case, a short shielding time is effective in facilitating planet growth in a multi-planet system via pebble accretion. So these results then again just highlights the importance of factoring in cluster evolution in studying planet formation in these active star-forming regions. Okay, so now on the top plot shows the number of massive planets formed per disk under 3 levels of FUV radiation strength indicated by color as a function of initial disk mass on the x-axis. So again, it shows that there are less number of massive planets formed in disks under stronger external photoevaporation. And the difference kind of becomes larger as the disk mass increases. However, on the bottom figure now shows the number of planets, final planets that are able to survive in the disk at the end of the simulation. And it shows that in the initially more massive disk regime, highlighted by the red shade, the results are now indistinguishable for different levels of FUV radiation. This is because planets initially formed in a disk are also subject to planet-planet interactions. So embryos in disks that are able to grow to planet masses can later on be lost due to these gravitational interactions between each other. Therefore, in our simulation, in more massive and weakly irradiated disk, for example, the blue curve in the shaded region, even though there are more planets formed in these disks, that also means that the planets are subject to more frequent gravitational interactions between each other. So a larger fraction of planets in these disks are lost, which then means the effects of external photoevaporation in suppressing planet formation are masked in the more massive disk regions. However, the caveat I would like to highlight is that the outcome of the planetary migration and these planetary interactions is very model dependent. So for a planet formation model that is more effective, for example, in retaining the planets, might produce different results. So it might actually make the effect of external photoevaporation more prominent in these more massive disks. It is basically just very model dependent. But what is clear is that the resultant planet population is an outcome of both earlier stage disk truncation by external photoevaporation, and the later stage planetary interactions once they are formed and grow more massive. So with this in mind, we plotted the final planet population evolved under different radiation environments. So first, we're looking at the inner AU region. Here are two examples of the final resultant population formed in two more initially massive disks. The x-axis shows the final semi-major axis, and the size of the circles indicate the final planet mass. The black empty circles indicates the planets that are lost due to gravitational interactions, and the red solid circles indicate the survived planets at the end of the simulation. And from these two more initially more massive disk cases, you can see that although there are more planets formed in the weakly irradiated environment on the left-hand side, more of them are also later on lost, as we just mentioned, so that there are practically no discernible statistically significant difference between the population in disks that are exposed to weak or strong radiation environment. So in most massive disk regimes in our simulation, the impact of external photoevaporation is kind of masked by the effects of planetary interactions. So planetary interactions are the processes that dominates the outcome of planet population in the more initially massive disk regime. However, in the initially less massive disk regime, like highlighted by the red region now for disks smaller than 0.1 solar mass, the impacts of external photoevaporation is still visible in the resultant planetary population in the inner AU. Here you can see that disks that are exposed to stronger FUV radiation would have less number of survived planets compared to the weakly irradiated disk case. So for disks with low initial disk mass that are exposed to strong radiation environment in a stellar cluster, cloud shielding time, for example, is still important in facilitating planet formation. In addition, we also discovered an imprint that external photoevaporation leaves on the wide orbit terrestrial planet populations in our simulation. Here on the left-hand side panel, we have a plot of the final planet mass on the y-axis and the semi-major axis on the x-axis for the final planet populations assembled in the fiducial disk mass of 0.1 solar mass. With a strong, the disk is again subject to a strong FUV radiation of 10 to the 5 G0. And from top to bottom, they include the final survived planets in disks that are shielded by the cloud for increasingly longer time from top to bottom. And then on the right-hand side is the number density of the planet population shown on the left-hand side. So we can see that in the region highlighted by this red rectangle, which includes the terrestrial planets between 0.1 to 1 Earth mass, and in the region of greater than 10 AU, we can see that there are more planets remaining in this region with increasing shielding time, or equivalently with weaker UV radiation. So finally, just for some takeaway messages, we have demonstrated that in massive cluster environments, they have important impacts for disk evolution and planet formation. We expect wide proliferation in massive stellar clusters, but cloud shielding time can protect the disk for at least the early initial stage of disk evolution. And that has important implication for planet formation via pebble accretion. So external photoevaporation acts to reduce the pebble mass reservoir in the disk, therefore it suppresses planet growth via pebble accretion. But we also show that for a multi-planet system, the final planetary architecture is a result of both earlier stage external photoevaporation of disks and later stage planet migration and planetary interactions. But overall, I wish I've demonstrated that it is important to study disk evolution and planet formation in the context of their natal birth environment, rather than only considering them as isolated system. And that is the end of my talk. Thanks a lot. And yeah, welcome any questions.
Do we have any questions in the room, or for the online audience? If you want to ask a question, you can feel free to type in your chat, or you can just raise your hand and I call you.
Alan, fantastic talk. I was just wondering, you mentioned that there were, the kind of a reasonable length of time for shielding was about a mega year, right? Has there been any kind of look into how, oh, is it muted?
No, it's okay. Go ahead.
Yeah, no, it's not muted. It's just the mute is for the room. The room is
all right, I see.
yeah.
Has there been any research into kind of the variance of the amount of shielding time between systems and how that would whether or not there's a very wide range of shielding times basically?
Yes, I'm very glad that you asked this question because now I can advertise my upcoming paper. So yeah, the kind of like a typical what we call kind of like a typical scale of cloud shielding in clusters that really depends on kind of like the initial conditions of a stellar cluster. For example, one of the most important property of the cluster that would decide this shielding time would be like the virial ratio of the cloud, right? For example, like that. So virial ratio indicates how gravitationally bounded the cloud is. So if the cluster is more gravitationally bounded, then obviously it would be harder for the cloud to disperse. Therefore, it would have a longer shielding time. And if it is weakly bounded, for example, it would have a shorter cloud shielding time because it's easier for the cloud to disperse. It would also, of course, depends on the cluster initial mass. So yeah, so the question of what is a typical shielding time scale for different types of cluster is a very interesting question to study. So my upcoming paper would take basically different stellar cluster with controlled different initial condition and kind of study how does that affect the cloud shielding time for disks in different types of clusters. So yeah, I guess yeah.
I was just going to say that that's kind of distracting to think. Look like I'm in an Ocean's 11 movie. I was God. It's very distracting. What was I going to say? So if you have larger clusters with more high mass, highly UV radiative stars, because they're going to be high mass, they're going to have be more kind of virialized, more more gravitationally dominated. That's going to kind of offset the effect of those more of those additional stars a little bit, I guess.
Yeah, so it would be like a balance between kind of more massive stars, but higher radiation, but also means potentially more bounded. Yeah, so it really needs so it would be balanced between kind of like the two dynamics and other factors. That's why doing like the hydrodynamic simulations of these clusters would that's why I'm doing looking at it.
Thank you.
So continuing the question, do you plan to basically you mentioned that you're going to simulate for certain example clusters. So would that be like Red Sea kind of regions? Or what ranges of examples are you exploring?
Sorry, what? Sorry, I didn't hear it very clearly.
So initial condition of those star forming regions that for your new upcoming paper that you were just talking about?
Yeah.
Yeah, I'm just wondering what kind of a range, parameter ranges you're exploring.
Right now we have like 3 clusters. There might be, so it's actually like a project collaborating with the Torch star forming group. I don't know whether you know, it's like Torch is like uh well-developed star cluster formation code. So it's my collaboration with them using some of their star clusters. So right now I'm kind of like working with 3 clusters of 10 to the 4 solar mass, for example, with like a virial ratio of 2, 4, and 0.8, for example.
Lama?
Well, thanks for a very nice talk. Also extending on this shielding question, have you considered any mechanisms that could provide shielding at a later stage in this evolution? Like the primary ones that come to my mind would be the material that's ejected due to external photoevaporations. For example, you have the ionization front, the molecular dissociation front in the way, or maybe material due to internal photoevaporation or something like that.
I apologize. It's a so sorry, the sound's a bit muffled. Can you just like can you please
Yeah.
Thanks for the nice talk. I was just wondering, have you explored any mechanisms that could provide shielding at a later stage of disk evolution? Like the material that's ejected from internal or external photoevaporation that itself could provide some shielding?
Do you mean self-shielding?
Self-shielding in a way as well, and probably also from internal photoevaporation or any other mechanisms.
So you mean later? Okay, so first of all, I should have clarified this. My models are not kind of like does not take into account of the internal photoevaporation. So my model only have external photoevaporation. Or internal photoevaporation, I guess, gets more significant in like the dispersal part of the disk. Probably after the planets are formed. Actually, yeah, kind of. So right now it's not like incorporated into the model yet. As in terms of later stage shielding, first of all, our model it doesn't really kind of like include self-shielding as well. I guess self-shielding in the context of external photoevaporation, well, the FUV photons that drives the external photoevaporation mainly, they're only really able to penetrate to the disk surface, and then in the PDR, they basically photodissociate. If they create a PDR region, okay, I'm trying to find the perplids kind of. Oh God, where it is. Oh, there you go. So like yeah, so the FUV photons, they're only able to penetrate to the disk surface and then launch a neutral PDR wind. So they wouldn't be able to penetrate further into the disk. So I'm not sure about then self-shielding in this context. But in terms of later stage cloud shielding, it is possible, and it's kind of like also like incorporating into the model as well, because the only way I guess that the disk can also later on be shielded is if the disk kind of like dynamically moves back to, for example, like denser cloud region that would be captured by the model. Oh, actually, now that I'm thinking, your question actually yeah, now it makes a lot more sense to me now. Sorry. I think one very interesting observations I remember by Megan, don't know, you must know her, is like a disc that's being photoevaporated. No, it's like a disc wrapped in a gas, like a much larger blob of gas that's being externally photoevaporated. And what?
There's like a globule kind, like in Korea, those big, blob of the gas.
Yeah,
Mm.
those kind of like globules. Yeah, so there's a very interesting case of a disk that is actually being wrapped under like being evaporated globules. So the globules actually then act to kind of like shield the disk from the radiation for some time. So there are these very interesting cases. So I guess that's kind of like a little bit of the self-shielding idea that you're mentioning. But yeah, but in my model, those effects are not accounted yet because it is right now just a very simple 1D viscous disk evolution. But those are all like very interesting cases to study, I guess.
Thank you.
I have one more question. So have you considered so in the case of flyby massive star, if your external photoevaporation ionizing source is moving, have you considered varying a UV field for each disk? If so, for instance, for the one that Gavin worked on, there is a walk away or flyby massive stars flying by YSOs. And very short time around them. Have you considered, so then FUV field strength will change over 100,000 years, 500,000 years during that time? Would that, have you considered those varying FUV?
So in terms of like the first part of my talk, when for the disk evolved under coupled to this cluster simulations, then that kind of like flyby of the massive source, that effect would be captured. But for the planet formation bit, right now, yeah, as I mentioned, right now it is a very simple case of a parameterized FUV field starting from a very low value and then just to a very high value. So it is not actually capturing any like the interesting dynamical effects of the real cluster evolution yet. So to study that, it would be like coupling planet formation model to the FUV tracks of from these cluster simulations. That can also be a very interesting project potentially for master's supervision actually. So yeah.
Okay, nice. Yeah.
Yeah, my question actually you answered a little bit. So my question is that you are modeling for single UV photo evaporation sources.
Sorry, sorry,
Yeah.
the voice is a bit muffled. I can't.
Yeah.
Sorry. Okay.
The pickup is very well.
The speaker is not so good.
First, no.
Yeah,
No, yeah, that one is there.
Okay.
Yeah, they're trying
Yeah,
to
so my
fix it.
question is if there are multiple far UV photo evaporation sources around this planetary disk, can you model that like not the symmetric, this like beautiful bullet shape, but the asymmetric. But you already answered your model is a simple. It doesn't really account any
Yeah.
variation. So, but is there a plan for? Is it possible?
Yes. So yeah, the very simple 1D viscous disk simulations, no one likes them. Like the star formation people don't like it. It's the planet formation people don't like it. Hydro people don't like it because it's like way too it's a 1D viscous disk is wrong basically. But like what can we do? We still have to use them. For modeling like proper like 2D or even 3D hydro disk with external photoevaporation, that would be kind of like proper radiative transfer hydrodynamics. Those would be like very expensive simulations. I personally don't have enough courage to do that yet, but Tom have been talking about my supervisor, now my kind of my boss, Serena's very good friends, Tom Howarth. He had like a past papers actually modeling 2D or even 3D disk with photoevaporative winds. He used torus code. I don't know whether people know about. It's like a radiative hydro code. He's always been talking about he should resume those simulations of 3D disk. So maybe I'll pressure him to do that.
Interesting. Another question is a little bit related to the earlier question you asked. So in the massive cluster, I assume the star formation in the massive clusters are more dramatic, and it will maybe blow all this material away. Of course, you explained that there are more stronger gravity, so there are more shielding happens. But I assume there are more exposed disks. So if there are more massive stars around this planet formation environment, and there less shielding would happen. Yeah, that was my very naive. Yeah.
No, you're completely right. This is also what I'm answering the previous question as well. It would be like a kind of like competition between much higher levels of radiation, much stronger feedback trying to disperse the gas, but at the same time, if there are more stars, they're if it's more gravitation bounded with more stellar densities, then it's also harder to disperse them given the same level of radiation. So it's a balance of all these factors. That's why I'm kind of like then using real radiative transfer hydro simulations right now to then simulate them and see kind of like which effects when, or how all of these interplay of different factors affect shielding time. So basically the answer is right now we don't know. That's why I'm trying to make a paper out of it.
Thank you. It was great talk. Thanks for your time.
Yeah, we're at the top of the hour, and thank you very much. And let's thank our speaker again.
Thank you so much.
Thank you, Lin. It was a great talk.
Thank you. Yeah, very nice to see you again, Serena.
Yeah, I hope to visit you